But let's get the slideshow set up from the current slide. Why isn't it? There it goes. All right. A great projection, but close to good enough, I think. I don't know if that's any better or not. Okay. Now, this is not where I had it set up when I went down to lunch. So it has advanced. There's where we were. All right. First thing before we go any further, are there any questions for anything we've done up till now? I'm not sure I'm going to get this in here, am I? No, I'm not going to get, well, I can almost get both of them that way. What I think I'll do is this and try to scoot from here. Sounds crazy, but I think it might. Okay. Any questions before we get started? I think finally this week the office hours are close to normal, but they have sort of a I guess it's bad news situation. Next week is the week of Thanksgiving. We'll be working Monday, Tuesday, and probably at least half a day Wednesday. But y'all won't. I mean, hopefully you will. I'll give you something to work. No. We have you get the whole week off for Thanksgiving. Okay? We have professional meetings Monday and Tuesday, and then I think day on campus on duty day on Wednesday. And then Thursday, Friday, the school's closed. So if you have any business to do with the school, you can get that done Monday, Tuesday, or Wednesday. But I would highly recommend, if you're going to wait till Wednesday to do it in the morning. Okay? Because when Wednesday afternoon gets here, people tend to start disappearing. Okay? And at some point in the afternoon, maybe noon, maybe 2 o'clock, or some point, usually the vice president will say, y'all go home. Okay? So don't put off any business you have with the college. You can get, someone will be here all day Monday, someone will be here all day Tuesday, and all offices will be open Wednesday morning, but I can't say how long. Okay? Now, some instructors and some staff, some faculty, faculty and administrators will be down in Montgomery. That's where the meetings are, Monday and Tuesday. Those of us that don't go, and I'm not planning to go, we will be either on Birmingham campus or this campus. They'll have us in meetings also. So when that's done, that'll finish sometime Tuesday afternoon, and then, like I say, Wednesday's a duty day. I'll be on one campus or the other, I don't know which. If I can get everything done from this campus I need to, then I'll go to Birmingham campus. But if I still have something to do that I need the stuff on this campus, I'll come out here on Wednesday. One or the other. All right. Any questions? Anything we've done till now? Okay. Sorry, it's taking a little while to get started here. I believe this is example 5, an elliptic paraboloid. Either of those look like they might be an elliptic paraboloid. This one. Both of them are paraboloids, but this one, the cross sections are ellipses. The cross sections of this, you see here's a parabola here and here and here and here and here. And then from this side here and here and here and here and here. Those are all paraboloids, but if you do the cross section, say across here, see these are hyperboloids like this. Okay? And down here they're like this. Okay? So yeah, that's hyperbolic paraboloid is elliptic paraboloid. Okay, so an elliptic paraboloid, sketch the contour map of f of x is equal to, goodness gracious, it's cold here. F of x is equal to, let's see if we can get this on the scroll side here. Here it is. F of x is equal to x squared plus 3y squared. It says comment on the spacing of the contour curves. That's what it says in our text. In the previous edition, it said these contour intervals were at 10. So I don't know why they say comment on them. But they drew the graph for us. But how did they do this? Okay? What the contour curves are is projecting the level curves, the horizontal level curves here onto the xy plane. Well, the only point of contact with the xy plane for this, of course, would be x equals 0, y is equal to 0. The f of xy, which is your z in this case, it would have to be 0. No way around it. And then no matter what values x and y you have, the z's are always going to be positive. From that point 0, 0, 0, they're all positive. So 0, 0, 0 is right there. That's the level curve. C is equal to 0. Z is equal to 0. Okay. Then do the level curves at any other value. And they said, let's do 10. But if you came up here, z is equal to 10. Now, I'm not sure that's that curve there, but let's just assume that it is. Then you have x squared plus y squared is equal to 10. Well, that's an ellipse, okay? With the major axis on the y. Now, this looks like the major axis is on the x. Let me see. No, I'm sorry. If you divided this by 3, then, yeah, that would be the major axis on it. So they got it right, okay? Basically, if this were equal to 10 here, the z is equal to 10, that slice up here, that forms this ellipse right here, okay? I'll twist that, the circle, the ellipse just a little bit, because it doesn't look like they're falling quite in the right place, but they're close. The intersections here would be, let's see, x equal 0, then 3 times y squared would be 10. I would rather do 12. Let's just imagine this is a 12 rather than 10. 3 times, this was a 12 over here, x squared plus 3y squared equals 12. If x equals 0, your y would be plus or minus 2. Okay? So let's just imagine this was a 12, not a 10. That'd be plus 2 here, minus 2 there. Now, of course, if y were equal to 0, then that would be the square root of 12 plus or minus the square root of 12. The square root of 12 is something between 4 and 5. No, I mean 3 and 4. Okay, square root of 9 is 3 and square root of 16 is 4. So this would be 3 point something and up. So yeah, that's looking like that would make sense now. You can do it with 10, just the fractions and things like that, so a little harder to imagine. So indeed, that's what 10 would be. This would be plus or minus root 10 here, and that would be plus or minus 3 and the square root of 3 and a third, or whatever that is, something less than 2. Okay, plus or minus 2 that way. So sure enough, and then you did. So this is a 10, 20, 30, 40, and 50. Now you could choose any intervals you wanted to. And frankly, to me, it looks like this first one might be a little bigger than it really should be, but maybe not, because your ellipse is the paraboloid is going up fairly steeply. So, any questions on how you draw that? Again, pick some points, okay? 0, 0, 0 is obvious, okay? And then it's also obvious also these two, some of these two is always going to be positive. So pick some positive value and then go back, set 1 equals 0, see what the other is, set this one equals 0, see what the other is, and you have the points here, 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 and here, and then draw the ellipse other value, go up here to 20, say, and at 20 you would be on this curve, if theirs is right. So this would be a 20 then, the z would be 20, and that would be same thing. If that equals 0, figure out what y would be plus or minus here and here, and then if y is equal to 0, that would be plus or minus 20, whatever that is, something between 4 and 5. Okay, and you just keep on going. That's how you draw your contour curves. All right. Then let's see if there's anything else here. Goodness gracious, I'm cold. The graph is elliptic paraboloid. As we move away from the origin, alpha of xy increases more rapidly. The graph gets steeper. And by the way, that's characteristic of contour lines. The further away the lines are from each other, the less steep the slope is. The closer they are together, that means you get steeper and steeper slope, and that's because it's going up quite rapidly. So for a small increase in x and y, you're going way up in z, so these curves get closer and closer together. Okay. Let's do example 6. Sketch the contour map of g of xy. Here it is, I think. X squared minus 3y squared. Okay? Okay. There is one more line down there. Interval 10. Now, this is harder to see on the map here because it's too tall here. But again, you do the same type of thing. Obviously, when x is 0, y is 0, the g has got to be 0, which is your z here. So that point is on the curve. Okay. Now, this is a little different because if y were 0, okay, then you can still have a y is equal to 0, meaning here's your y-axis. That's always 0 here. What is x and z doing then? Well, that's a parabola, and y is 0. Of course, the base, the vertex is 0, but it's a parabola that goes up like that. So here's your y is equal to 0 here, and where that is the case, your, I think I'm going to have to scoot this up so Ashley see her good. All right. By the way, I didn't ask this question before. It just dawned on me I didn't. Did all of you get your second test? Okay. Because I think I handed those out last time. I think it was second test, wasn't it? I know they're in here somewhere. Okay, close. Got it. How many? 1, 2. Actually, you get one? Okay. I thought someone said they were going to give you one. Yeah. That's 2. And these were from chapter 13. And I believe it goes down the line. First 2 problems are section 1, second 2 sections, 13.2, next 2 sections, 13.3, next 2, 13.4, next 2, 13.5. That was how, yeah. Okay. So 2 questions each section, first 5 sections. Okay. All right, we were looking at this. What would the name of this one be? Vertical cross sections, they have a different word for it, are parabolae. So it's a paraboloid. But this one, the horizontal contours, we're going to call them, but they would also be your traces. Traces, that's the word I was looking for, would all be hyperbole. So it's a hyperbolic paraboloid. also sometimes called the saddle point. If the horse went under here, your leg would go on both sides. Okay, so it's like a saddle. Okay, what we're looking at is where y is equal to 0, then you have g is equal to x squared. So I think to get y is equal to 0, you look down the y-axis here. Y is always 0 on the y-axis here, and you would get in the xz plane, here's x, there's z, xz plane, you would get this parabola right here. It's not the one that's dark, but this one right here that goes through the origin. Okay, that's the parabola. X is equal to z is equal to x squared. Okay, now if you go, yep, going the wrong way. All right. You go x equals to 0, then you have, z is equal to minus 3y squared. Okay? Well, that's a parabola opening downward. So x equals 0, that would be the yz plane here. All in the yz plane, x is equal to 0. So if you're looking down the x-axis at the yz plane, then I think this is it here. It goes up here, down there, and it comes down like this. So it's a parabola opening downward, and that's a pretty steep parabola because that coefficient of 3, that's a vertical stretch downward. Okay? Whereas this one here, that's a more normal parabola. Then you come away from that, and you've got parabolae that change their positions. And that's what you're looking for too. But the contours here, we're looking at the slices parallel to the xy axis as you're going up z and down z. So let's just imagine this plane, the xy plane, go up a little ways here. Well, the first thing I see coming up here is this parabola here. You don't see the back leg of it, but you see it coming here, and you see the back leg here, and don't see the front leg, is coming around here. That forms this hyperbole here. This is the positive wing, there's the negative wing on it, negative x. Okay? If you came out the y-axis, okay, I'm sorry, if you went down the xy plane, went it down one, then you have a parabola, hyperbola back here that's going that way, and this one's coming this way. So that would be on the y-axis, going like this. Here, it's where I think they've got something backwards here. They say, yeah, no, they got it right. G of xy is increasing here as you go up. C is increasing, then your, and that's your G of xy, increasing here. You have hyperbole going out this way, getting greater and greater and greater. And when you slice them going down like this, you get the hyperbole going further and further out this way. So G is decreasing going this way, increasing meaning getting greater here and going down there. That's exactly what you've got. Now what I'm trying to see to show you, here it is. This line right here bisects the positive y, negative x axis. You see that line right there. And this line right here bisects the positive x, positive y, negative x, negative y. So it goes back here. So here's that line. That's this one right here. Is that line. And this one over here is that line. Those two lines, that z is equal to 0, you have the origin there, but you also have a ray that comes out here, there, here, and there. Okay. And that's also on the xy plane. is equal to 0. So C is equal to 0 here, plus 10, plus 20, plus 30, plus 10, plus 20, plus 30, minus 10, minus 20, minus 30, minus 10, minus 20, minus 30. Each slice going down, let's see if we can about it. 10, 20, 30. That's coming up this way. And going this way, 10, 20. I'm going to have to go up one. Yeah. 10, 20, 30 going this way. Increasing. Going up. Does that make sense? A lot easier to wave your arms on than to draw yourself. Okay. Kind of miserable. But this shows what the contour lines are. Now, what I kind of like to do, just for my own benefit, is maybe, since you got colors anyway, do the decreasing ones in a different color from the increasing ones. That way, I've got a better visual going on. Just looking at that, without the words here, I don't know what kind of pattern that is. It's pretty bizarre. But you don't know that it's that pattern unless you know these are decreasing. Of course, if you have the C's equal to plus 30 and minus 30, that helps clue you in. But you see, without also listing here, you don't know what direction they're going unless you have the color. I think that's a good idea to do. All right, so that was example 6. Sketch the contour map. They did, thank you very much. The level curves have the G of XY is equal to C, so you just do these various values there and plug them in. Okay, oh, and by the way, these two lines here at C is equal to 0, the two I mentioned, they give the formula for them. X is equal, because again, C is equal to 0 in this equation here, and if 0 is equal to that, this is x plus the square root of 3y times x minus the square root of 3y. This is x. Let's see if I can get these right now. And again, this to me looks a little faulty. This looks like, I actually said it, I didn't mean to. That looks like it really does actually bisect these angles here. They shouldn't, because this is square root of x plus square root of 3y is one of these. That would be the one with the negative slope. I think that's this one. And, well, phrase it this way. X equals plus or minus square root of 3y, and 3y is equal to plus or minus the square root of x in the opposite order. And basically you get a line x equals plus square root of 3y would be this way, and you got plus or minus it would be the one back there. And Victor's here. Deal. Good attendance today, folks. Only missing Javon and Jonathan. Okay, hopefully one or more of them will show up. So that was example 6. And the picture is on the next page, the one we've just been looking at. Now let's do example 7, which is sort of, this one skips example 7, I think, but I'm not sure. Let's take a look. A contour map of a linear function. Oh, yeah, we are skipping it. Now, this is figure 14, so I think we are okay on this one. I think the next thing they talk about is it seems like the book is not quite put together the same way the slides are, but I think they're supposed to be. All right. Sketch the graph of f of xy is equal to 12 minus 2x minus 3y. And the associated contour map with contour interval m equal 4. That's what they ask us to do. Okay. Now, this map here, in other words, z is equal to 12 minus x, 2x minus 3y. Where I would begin is that xy equals 0. X equals 0, y is equal 0. Well, then you have z is equal to 12. So where the cross section of the x and y things are, both of them equal 0, there you are at 12. So that makes sense. Okay? Now, if you were to set x and z equal to 0, then that would have you 3y is equal to 4, right? If x is 0 and z is 0, then you have 0 is equal to 12 minus 3y. Add 3y to both sides. 3y is equal to 12. Y is equal to 4. There you are. There you are. Okay. Y is equal to 4 right there. Okay. And then if you had y is equal to 0, then you have mz. Y and z is equal to 0. You have 12 minus 2x. What is equal to 0? In other words, 2 is equal to 2x equals 12. So x equals 6. There you are. X equals 6 when y is 0 and z is 0. So that gives you this triangle, and that triangle pretty much defines a plane. A edge of a plane. And how do you know it's a plane? This is to the first power, that's to the first power, that's to the first power. Those are all lines here. So if you wanted to take it one more step, if you set z is equal to 0, then you have in the xy plane 2x plus 3y is equal to 12. 2x plus 3y is equal to 12 is that line right there. And you can play around with graphing this on the, I'm sorry, it's this line right here. 2x plus 3y is equal to 12. That's this line here. So it's 2 times 6, yeah, that works. XY plane, there's that line. And then so where you can do y is equal to 0, and then you have 2x plus z is equal to 12. That would be the line. Yeah, it would be this one right here. This is the xz plane. Second? Yeah. And then x equals 0, you have z equal 12 minus 3y, or else 3y plus 12 is equal to 0. They equal to 12, and that would be this line right here in the yz plane. So again, we have our slant, our plane going up like that. Okay? Which basically you have to do that separately. Once you have the 3 points, just connect them. You know they have to be straight lines. Okay. The contour map, which should be 2 words, not 1. They got it right in the book, but wrong on the slide. It says with intervals m equal 4. We did the one where x and y is 0, okay? Yeah, that's this one right here. xy equals 0. F of xy equals 0. Where c is equal to 0. Okay, that's this line right here, connecting plus 6 minus 4. And then if you had c equal 4, that would be 4 here. So that would be, I would rewrite it like this. Oh, as soon as I do my pen, it's going to disappear, or shrink anyway. And let me get my black pen back. And I would say 4 is equal to 12 minus 2x minus 3y. That's when c is equal to 4. The next contour line up. So I would rewrite this as 2x plus 3y is equal to 8. Okay? And there you have a y-intercept, so to speak, of x-intercept of 4, and a y-intercept of whatever that would be then, 8/3. Okay? So that next one would be x equal 4. So that looks like 2, 4, 6 coming this way, and that would be 4/3, is it? Let me think. Yeah. I I think 4/3, 6/3, which would be 3/2. No, that's not coming out right. Yeah, that would be. And then another 4/3, 4/3, 8/3, and 12/3, which, yeah. So that would be, the next line would be, or that would be what that one would be. The next one down is equal to 8. 8 is equal to 12 minus 2x minus 3y, and that would be 2x plus 3y is equal to 4, and that would be this line right here. Okay, your y-intercepts would be, your x-intercept would be 2, 0, which is right there, and the y-intercept would be 4/3 right there. So that's the that one. Now they did do one other. Well, okay, when c is equal to 12, 12 is equal to 12 minus 2x minus 3y. Well, we know what that is. Subtract 12 from both sides, you get 2x minus 3y is equal to 0. Well, that's going to be the line that goes, that's this line right here. If I could draw a straight line, it goes through the origin and with a slope of 2/3. Yeah. Okay. All these have slopes of 2/3, by the way. No, negative. Wait a minute. That's a plus. Sorry about that. Negative 2/3. Okay. All these have the same slope. They're all parallel to each other. And then they did one at c is equal to minus 4. So let's do that one too. Minus 4 is equal to 12 minus 2x minus 3y. I would rewrite that as 2x plus 3y is equal to 16. And that would be this one down here. The intercepts there would be 8 here and 5/3 there. No, that's not right. 12/3. 16/3. Okay, there. So that would be there. Now they continue on and do, and even the, notice here, it doesn't stop. The plane keeps going. This just gives this little triangle with those points. But the plane keeps going back that way and out this way as you come down. So they did 16 and 20, and you get this contour. The slopes are the same because the x and y coefficients are the same. So what was the next one? 16. 16 is equal to 12 minus 2x minus 3y, and that would be 2x plus 3y is equal to minus 4. And that would be the line up there, okay? Have a slope of, the x coordinate here would be negative 2, 0, and that would be negative 4/3, 0, okay? Or, sorry, I said it backwards. 0, negative 4/3. And then one more, that 20, that would be 2x plus 3y is equal to, when you had that would be minus 8 then. So that would be a minus 4 here and a minus 8/3, which would be, 8/3. Yeah, 8/3, which would, yeah, minus 8/3 there. Okay, but that's how you get to draw those contour lines. Parallel lines, because this is a plane, and every contour just maps out another line down onto that plane. Pretty exciting stuff, isn't it? Okay. Now, this is where the next picture comes in, which I thought was out of order, but I guess they're right. Pretty picture here. Looks slightly different from the one in the text, and I think I have some guesses of why. It's the Mount Whitney Range in California with the contour map. Now, anything special about Mount Whitney? Anyone know anything about that? The highest point in the continental U.S., the contiguous, let me say that way, contiguous U.S., the contiguous 48 states. Mount Whitney is the highest point in that. Once Alaska became our 49th state, it was no longer the highest point in the U.S., because now it's Mount McKinley. I think it is in Alaska is the highest mountain. So this is Mount Whitney in the contiguous 48 states. It's the highest point. This is a range in California, and obviously there's a nearby mountain almost as tall, and then one almost as tall as it, and then you have another one there. And now coming this way is a little deceptive because this is a mountain in the foreground. So it may not be nearly as high as what it seems in the picture here because it's much closer to it. Now, the thing that I find disturbing here, but unfortunately probably is true, it could be the time of day these were taken. I don't see, I see a copyright listed, but not the date of the copyright. What I fear is this one is probably taken 4 to 6 years before the one in the book. And if those were the same time of year, it shows how much of the glaciers may be lost. Because the one in the book, you'll notice, has a lot less snow. Now, it could be it was just time of year, but I would not be at all surprised that if any of this was permanent snow, as in glaciers and stuff, which it really doesn't look like it would be, except possibly in the valleys here. Now, I don't even know that for sure. And those, even that, it looks a lot less. But again, that could be just different times of year. But they look like they were taken with the shadows almost identical, but a lot less snow. Okay, sad but true. Now it could also be the drought conditions dried up some as well. It may not just be temperatures. All right. With that said, let's take a look at let's see what it says. How can we measure steepness quantitatively? Let's imagine that z is equal to f of x, y as a mountain range. In fact, the contour maps, also called topographic maps, contour topographic, that means the same, are used extensively to describe terrain. And the right-hand side of this is exactly the same in both conditions here. And if indeed you can relate these two to each other, I think you can. Just trying to piece together what their markings are here. It's really hard to see the contours because they're so light on here. Yeah, this seems to be Mount Whitney right here, the tallest one right here. And you see the enclosed contour there, the peak is somewhere right there. Now, what this is the ridge line, is what I call it. They have a name for it geologically. It's literally that peak ridge that goes up and down, and I think that's what that is standing for. Okay, so here's Mount Whitney, near the top right there. The top would be somewhere near the center of that. There, and then you got the contours going around it. But at some point, let's see if we can find this one here. Let's plug it in. These are so hard to see. I cannot pick out that next one. Let's see if I can in the book. That's almost worse. I think it's somewhere right in here. You have another enclosed circle. It's not circle, but closed contour lines. I mean, equal elevation. There's mountain peak in between them. Okay. Now down here, and you can't see these in the map, these look like lakes. Okay, probably glacial lakes. And here is Jonathan. Okay, oops. I got to put you in the right place here. I need to put a P there, not an A. Okay. Only missing Javon. So glad y'all are here. Way to go, team. Missing Javon. Okay. And these are lakes here. They're also surrounded by contour lines, but that's because this is a depression. These are contour lines around an elevation. These are around the depression. I'll pick those out because they show water like that. Contour map wouldn't necessarily, except they colored it in. So somewhere over here is another enclosed area, and then probably another one. The lines are so hard to tell there. Okay. And then they've drawn the other line on there that really confuses the contour, but they drew that in to be the dividing line. And by the way, they do call that a divide. That's exactly what they call it. That water on this side of the mountain flows this way, and water on the other side has to flow the other way. So that makes a little divide here. Of course, the continent has actually two divides. Okay, somewhere around Montana, Colorado, and coming down there is everything to the east of that divide flows toward the Atlantic. Everything to the west of it flows toward the Pacific. That's the continental divide. But then there's also another one along the Appalachians where everything to the west of it flows into the Mississippi, into the Gulf, and where everything east of it flows directly to the Atlantic. And there's another continental divide there. This is a smaller divide where probably on this side maybe it flows toward the Colorado River, and on that side it flows to the Pacific Ocean. Ultimately, Colorado River also makes it into the Pacific Ocean, but it comes this way before it goes that way. Okay, so you see, you use these contour maps or contour lines or all sorts of applications on them like that. Have any of you ever heard of the sport called orienteering? Okay, that's the sport that, oh, you have? Have you done it? Okay. But orienteering is when you get out into a place where they've marked off a course, okay? And they've marked it off both physically on land, but all they give you is a contour map, okay? And showing you where the things are there. You have to run the course in the order, and sometimes it's doubling back and crisscrossing all things else, but it's not, the best route is not necessarily the straight line between target 1 and target 2. Okay, it may go through a deep ravine this way, but if you go around this way, you stay on the contour. So you have to be able to read the map and estimate what's going to be the quickest way for me to get from here to there, not necessarily the straight line, because that straight line doesn't show this, whereas this curve here may be actually a level curve, and they call them level curves, like we have. So that's contour map, also called topographic map. Okay, you also get a compass. You get the map, a compass. I think that's it. That's what you take off and you run the course with that. And you have some sort of device that if you get close enough to the thing, it clicks you in, and if you know you clicked in, you run to the next one. We had a kid that lived with us from Italy, and he did, in fact, he's on the U.S. National team for orienteering. He's a U.S. citizen. He was born here, but he was from Italy. And he actually does the races in Europe every summer. All right. He's now working over there as well. But let's see if we can find where this is. Is this example 8, or is this the conceptual insight? No, this is example 8. Average rate of change depends on your direction. Didn't have this when we were in 2-dimensional space. In 3-dimension, it certainly does. And that's sort of that contour type stuff I was talking about. Compute the average rate of change from point A to point B to point C and to point D. Okay? shown in figure 16, and they said B. Where is 16A? Oh, I see. Wait. Conceptual insight. Oh, no, even before that. In your text, right under the picture of Mount Whitney Range in California with the contour map, figure 16A, that's the one here. And let's see if, I don't know for sure if I can blow up. I might be able to get it all on there. Look at that. Okay. Upper left. Okay. So it's 2 points P and Q in the XY plane. That's down here. XY plane, that's the contour NZ, but plotted onto XY. So here's point P and point Q in the XY plane down here. They correspond to this P tilde, I think I would call that up here, and Q tilde, which is up there. Now here on the contours, they look fairly close. When you do them there, they look like there's a lot more distance between them because you've got a lot of elevation change going on there. The contour interval is 0.8 of a kilometer. So from here to here is 0.8, from here to here is 0.8, from here to here is 0.8. Each of those is 0.8 of a kilometer. So you're moving laterally, 1, 2, 3 times 8 is 2.4 kilometers. The horizontal scale is 2 kilometers is, I guess, this on the Z. I don't know. That's a strange way to express it there. Is that the same way it does on the book? Yeah. I'm sorry. Contour intervals are, 0.8 elevation change. The contour intervals this way, and I don't know. Just looking at this, that looks like that's about 2 kilometers there. So how much elevation change do you have? 2.4 kilometers elevation change because you went up 0.8. 0.8, 1.6, and 2.4. Okay, so that was your vertical change over approximately a 2 kilometer thing. So 2.4 divided by 2 would be a 1.2 to 1 scale. So that's a pretty good slope. Better than 45-degree slope up. That's pretty major. Okay, so I think that's all they're talking about there. And they just show the symbols, but they don't actually give you any numbers for them, except on the map itself. We'll discuss the idea that rates of change depend on what direction coming up in 14.5. And just a little comment here, if you went from P here to some P1 over there, but stayed on the curve, you have absolutely no elevation change. Of course, if you cut across from it this way, you'd be going up in elevation and then down in elevation, even though you look like you're on a straight line here, okay? So this is a flat line, this is going up and then coming back down. I think that's all they were getting at. So now we're ready, I think, for, okay. Here is a more realistic picture. This is a computer simulation picture, which is easy to talk about that way. Here would be another one. Here is this hill in the middle, mountain, whatever you want to call it. You're near the base of it at A. If you're going to B, what's the question here? Compute the average rate of change from A to B, and then to C, and then to D. Okay. All right, got it. I think I understand what we're saying. If you're going from A to B, your elevation change is from 1,000 or 1,000 to 1,100. So how much elevation change you have? 100. Okay? And then they say here, whatever, and these are in meters. So if you go A to B here, they're telling you that's 200 meters. Okay? So that's a 1/2 slope, or 0.5 slope. Okay? I think that's what they're asking for. Compute the average rate of change. You're going up 100 meters for every 200 meters you go 0.5 slope. Okay? How about from A to C? What elevation change? Also 100. But now, they say this path is equivalent to 400 meters. So that's an average of 1 to 4 slope. Okay? And again, average is sort of in there because this looks pretty irregular. Sometimes you might be going flatter and stuff, but on average about a 1 to 4 slope. How about going from A to D? 0 slope because that's along the contour. Everything there is at 1,000-foot elevation, or meter elevation, I guess it is. So you're not traveling any kind of a vertical increase. Okay? They didn't even give you the deep part, but you don't need it because your numerator is 0. Okay. Oh, the book is different. Okay, sorry about that. In our text, it's not that mountain. It's a figure that's whose elevation, the contour lines are at 100 feet rather than 50 feet. Okay? So if we were to relate those to each other, this would be 2,000, 2,100, 2,200. So that's a 200-foot climb and 200-foot lateral. So that would be a 1-to-1 slope. Yeah. And then this one was also a 200-foot climb, but a 200-meter climb and 400 meters. So that's a 0.5 slope. And then this would be a 0 slope. Because no elevation change. Who knows what your horizontal distance is. It looks like in the neighborhood of 400, but it may even be less than that. Yeah, it looks like, well, it's not far from 400. But who cares what the denominator is? The numerator is 0. Okay. Sorry, different pictures. When we walk up a mountain, which I usually avoid at all costs, the incline at each moment depends on the path we choose. If we walk around the mountain, our altitude does not change at all. On the other hand, at each point there is a steepest direction in which the altitude increases most rapidly, going up the mountain, but also possibly going down. On a contour map, the steepest direction is approximately the direction it takes us to the closest point at the next highest elevation curve, level curve. We say approximately because everything depends on what varies between those elevation curves. And you can't always tell looking at the map. There could be little boulders in the way that you have to go up and down to get across. Okay. Is there another figure here? Yes, there is. Now somehow the figure numbers have gotten off too, it looks like. This is figure 17 in the text, and it's 18 here. I think the previous two was 16 and 17. Now they've made them 17, 16A and 16B. Okay, something. All right. So this is figure 17 in the text. Okay. If you got an older text, it's 18. All right, what are we to do with this one? Okay. So, I guess what they're saying is, when you're standing right here, the closest direction to that next level curve is there. I mean, that's the closest. Still pretty far apart, so you don't have a great slope to go, but that's the steepest slope you can go from this point. If you go this way, you're 0 slope this way, so that's going to be steepest. Without having another contour line here, it's hard to tell, but normally the steepest down is exactly the reverse of that. Okay, if you come over here, boy, yeah, I guess that is. The steepest slope is in that direction. Here is level, there is level. Steepest down to me here would be probably this way. other words, the shortest distance to the next contour line is your steepest ascent or descent. Okay? Over here, if you're at this point, the steepest ascent would be right here. Anything else would be longer, and the steepest descent actually looks like it would be here. Maybe not quite in line with that, but pretty close. Up here, steepest descent obviously is here. So what that gives you, by the way, is awfully close to your perpendicular. This is not perpendicular. I think maybe that's closer to being perpendicular from the upper one. And it looks like that's close to perpendicular there too. I think if that is in fact the case, perpendicular from the upper end, that's always going to be your steepest curve. Not from the lower end, because that's obviously not perpendicular from this tangent line, but from that tangent line. That's your steepest. Okay? Now, so in this case, if you were to go from P to Q, if you go the steepest route, the closest point, shortest probably too, without any major variations in between there, then you're going this way. Okay, each one of these is progressively the closest point to the next curve. Now, obviously, in nature, it's probably not that way. That's probably a lot smoother of a curve, but it's still not far off from that. This path over here may actually be an easier path to do. Not nearly as steep here, or here, or here, or here. And you get P to Q there. But you go a lot further to do it. But if the steepness slows you down enough that you can go this at a much faster rate, that might be the more efficient route to take. May or may not. You just have to use your contour map to see. Especially if between the contours here there was a ravine that went way down and then came back up here. Not the best way to go, okay? So your contour map would have to have a little more detail to tell you the ravine was there. All right. Does that make sense? Okay? So the path of steepest ascent is the path that begins at point P and everywhere along its way points in the steepest direction. We can approximate that path of ascent by drawing a sequence of segments that move as directly as possible from one level to the next, and those two showed that. I really dislike the way this book has these opening touchy-feely sections that talk about things without giving you any real math to them, okay? We're going to use all this later, okay, when we talk about gradient. That's exactly what we're talking about with the path of steepest ascent, okay? That's your gradient. But they're making you feel good about it, I guess, first, and then they're going to hit you with the math. To me, the math makes me feel really good, so why don't they hit me with that first? Okay, never mind. All right, what if we have more than two variables, okay? These have pretty much, see, your contour map sort of takes out the third variable and puts it on an XY plane. That's what maps are. But if you could picture this in 3 dimensions, yeah, it's a lot stranger looking maybe. There are many situations where a function of more than 2 variables is necessary. Here's one. If you wanted to keep track of temperature at various points in a room using the function t as a function of x, y, and z, okay? Well, let's just take this room for instance. There's a valley right up there. I mean, that's cold air coming out of here. And the coldness, you know, permeates from there. I bet you the warmest is right over here. Archie isn't it now? Okay? It likes the warmth over here. So if you were to plot each point in the room and the temperature, I mean, you would have to, it would make you have an X, Y, and Z, so 3-dimensional space, and at each point in space, you put a thermometer there and find the temperature at any time and, you know, hopefully freeze that in time to get a full picture of it, okay? Well, then you're not talking about level curves. You're talking about level surfaces, okay? Except the term level sort of loses a little bit of meaning. What you mean by that is equipotential surfaces. But we don't, this isn't physics, so we're not doing that. But that's really what you're talking about here. Let's say you had a heat source in the middle. Perfectly still room, no vent blowing in and stuff like this. Then the odds are your heat contour would look like this. The hottest would be right in the center, and then as it goes further out, your temperature drops off until you were a sphere. Okay? These are then would then be your, I would call them equipotential surfaces. Okay, which I think is a better word. They call them level surfaces. What's level about a sphere? Okay, nothing is really level there, but they mean equal. Something is equal there. Isothermic surface. That would be the best way to refer to this. Iso meaning same temperature at all points. Now they're not talking temperatures here. I'm just using that because that was their last example. That's the origin 0, 0, 0. This would be x squared plus y squared plus z squared is equal to 4, 9, because this is r squared, r squared, r squared. So radius 1, 2, and 3, which would be equal to 1, 4, and 9. Okay. Now, if indeed that's what you had, either a sink here, meaning a low point, a high concentration of dry ice, okay, there, and perfectly still room, then the temperatures would be going down as you went in there. Or if that was a point source of heat radiating outward, then your temperatures are going up as you go away from it. If these were temperatures, whatever they happen to be. So those would be more than two variables. 3 independent variables there, x, y, and z, for constant t or some other thing. But you see, before we're using the third dimension as our surface, now the surfaces, the 3 dimensions are all occupied with the variables, and you have to just draw the surfaces in. Okay, these should look familiar, right? This is example 9. Describe the level surfaces of these let me blow it up so you can see it better. We can't get it all on one screen, but we can get 2 of them on one screen. Okay. Level surfaces of g of x, y, z is equal to x squared plus y squared minus z squared. Yeah. Okay. Now, when this level surface is a positive number here, so this is x squared plus y squared minus z squared is equal to some positive number, say 1 or 2 or 17 or whatever it happens to be, then this is going to be, what do we call this? A paraboloid of 1 sheet, right?
2 sheets is when it's
Yeah, and we'll get to that one in a minute. That is if that C is positive, okay? So this, whatever in X, Y, and Z, you see, if Z were 0, then you've got ellipses here, okay? Or when Z is constant, you got an ellipsis, okay? Whether it's 0 or constant, you got an ellipse. If Y is 0 or a constant, then you've got hyperbole in this direction, okay? XZ is hyperbole. If X is 0, then YZ are your hyperbole. constant going out or over. Vertical traces, those would be hyperbole. Okay? Horizontal traces are level curves, those would be ellipses. Okay? Z is constant. Now, if that C were not greater than 0 but equal to 0, in that case, 0, 0, 0 would be 0, and that would be the only way you get that to happen. Well, not quite the only way. If y were 0, and anytime x is equal to z would also be 1. And that would be if y is equal to 0, that would be the xz plane here, and that would give you that line that crosses like this and the line that crosses like that. Okay? And x equals 0, that would be the yz plane, and there's one line that crosses here and one line that crosses there. Okay? So there are some other values there. I mean, that you could get g is equal to 0. Okay? But it would form, what do we call this one? The shape? Chemistry labs? You may not have had chemistry labs. These are cones. Oh.
Yeah, I was thinking it was a cone because the cone isn't actually just this.
Yeah, but a cone, a true mathematical cone, goes in both directions. Okay. Chemistry is only one. Okay. Sometimes almost get a really small ellipse in the center there, then you have an hourglass. Okay, so if you have 0, nothing goes through those are cones. Whoa, that's not the one I meant to do. Okay, let me go back to this. Okay, now this is if G is equal to C, C is negative. That would be x squared plus y squared minus c squared equal to a negative number. Then you have a, say again?
Two sheets.
Yeah, a what? Two sheets. A purple and 2 sheets. Very good. And then when you put them 3 together, you can see as z is positive, you're getting figure out this way. Z is 0 is there, and z is negative, you're getting these two sheets. And the more negative they get further and further apart. So those would be level surfaces, not level curves, but level surfaces at various values of c. Get harder and harder to imagine. Okay, but I think that's it for 14.1. A lot of blah, 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 okay? Ooh, yeah, this is what it looks like, okay? Now, let's look at the preliminary questions. I think these will be mostly conceptual. Let's see. What is the difference between a horizontal trace and a level curve? And these are very similar terms, but slight different meaning. Horizontal trace and a level curve. I'm not sure they're actually defined. Yes, they are. They are defined in this section. I was thinking this was back in 12.6, but they are actually here. Page 742, right at the bottom of the page. Okay. These are the horizontal traces projected on the XY plane that makes the level curve. Did I say I'm right? Yeah, I believe that's right. Yeah, the level curves are those horizontal traces, which are your horizontal intersections of planes above, say, the XY plane, where they intersect the surface you're dealing with, and then the level curves when you plot all those on the XY plane. These are the horizontal traces. Those are the level curves. Okay. How are they related? Third cousins twice removed. No. How are they related? They're exactly the same curves. It's just where they are. Are they up on the surface or are they plotted down on the XY plane? Now that's my definition. Let's see if they have a little more mathematical definition in the back. This is 14.1 preliminary question. Same shape, but located in parallel planes. That's a pretty lousy description. It's not the first part of the answer. What's the difference between? Well, it sort of is. I guess that can handle for both of them. What's the difference between them? The horizontal traces are plotted actually on the surface of the curve at different values for your vertical axis. Okay, whereas the level curves of those same shapes, identical shapes, plotted onto the XY axis. So on the parallel plane. Number 2, describe the trace of, let's see if I can find I'll do it here. Describe the trace of f of xy. It has nothing to do with this here. F of xy is equal to x squared minus sine of x cubed y in the xy plane, xz plane. Okay, they put the dash in between the z and the plane. I'll do it there. I don't know. Describe the trace of that in the xz plane. So if you're in the xz plane, what's what? What's one thing you know right off the top? Y is 0, exactly. So you're in the xz plane. So let's just imagine these globes, these spheres right here. You're in the xz plane. Y is equal to 0. So you're just looking at the xz plane. So describe the trace of that function there where the y is 0. Say again? That would be z is equal to x squared. Because if y is 0, then the argument for sine is 0. Doesn't matter why x cubed is. That's still 0. So that would just be z is equal to x squared. What would that be? Describe that. It's a parabola like this. Yeah, x and b plus or minus doesn't matter if y is with the z is always constant. That's it. Okay, that's how we described it. Let's see how they describe it. They say the parabola x is equal to y, z is equal to y, x squared, blah, blah. That's all they say, and that's exactly what we said. Okay, number 3. Is it possible for two different level curves of a function to intersect? Yay or nay? Two different level curves of a function to intersect. Okay. No, and that's a good thing not to have. Because a function for any input you have different outputs, right? That's the definition of a function. Even if the inputs are multiple, okay? So for any input, any point on, say, the xy plane, if xy are your input, your independent variables, z is your dependent. For any point on there, there's one and only one output. So how in the world do two contour lines, isn't that what they ask? Level curves intersect. That would mean that this combination of xy and another combination of xy give you It gives you, it just doesn't work. No. Let's see what their explanation is. We agree the answer is no. Let's see what the explanation is. Not possible. They really explain it well. Not possible. Exactly. Number 4. Describe the contour map of f of xy. Here's another one. F of xy is equal to x. Describe the contour map of f of xy is equal to x with a contour interval of 1. With contour interval 1. Describe that contour map. Yeah. Okay. So let's sort of, here's your z-axis, your y, and your x. So there's your x-axis here. And everywhere z is the same value as the x. Okay? So when x is 1, z is 1. When x is minus 1, z is minus 1. When x is 2, z is minus 2. When positive 2, yeah. So what in the world is this looking at? Describe the trace of that in the xz. Oh, I'm sorry, looking at the wrong question. Describe the contour map of that with a contour interval of 1. And by the way, when x is equal to 0, z is equal to 0. Okay, so 0, 0 is there. And by the way, all of that line, the y-axis is also there. When x is 0, z is 0. That's true everywhere on the y-axis. So it's not just a point, it's the whole y-axis there. Okay? And then when x is equal to 1, and where x equal 1 would basically be a plane here, and z is also equal to 1, that would just be this point right up here, and 2, 2, and probably got that one a bit too high, and negative 1, negative 1, negative 2, negative 2. But then, too, every one of these places you have an infinite number of y values as well. So isn't every one of these a line just like the y-axis is here?
That looks like stairs.
That's what?
Looks like stairs almost.
No, but not a stair. That would be, it would be a plane that went, it sliced right through whatever value x, y. It comes down the xz
It's just like
identity function.
Yes, the identity function, but just a plane.
It's a plane that makes that cuts through like that, exactly bisecting this quadrant right here, and then bisecting one down there. So it's that plane. Okay, that's what we're dealing with. But describe the contour map of that with a contour interval of 1. Well, the contour map is going to be on the x, y axis. So I just drew the 0, 0. Then at on the x, y axis, that would be 1, 2, 3, negative 1. Yeah, these would be parallel lines, exactly 1 unit apart. I guess that's how you describe it. Okay, let's see how they describe it. Okay. 14.1. The vertical lines x equals c, the vertical lines x equals c, with a distance 1 unit between adjacent lines. Oh, wait. vertical lines x equals c with a distance 1 unit between adjacent lines. Why vertical lines x equals c? I don't get that one. Oh, yeah, okay, I see what you mean. If we draw the xy plane like that, that means take this and do it like this, where y is up and x is horizontal. Yeah, those are vertical lines, and they're 1 unit apart. Okay.
Same thing as there.
Yeah. See, I was thinking z was vertical, and I said, how do you get that? Okay. 1 unit between adjacent lines. Yeah, that's exactly what we said. Number 5. How will the contour maps of f of xy equal x and g of xy equal 2x with a contour number 1 look different? Well, we just described this one. Now let's see if we can do it. What color you want? Say again? Yellow. You can't see very well, can you? Okay. I don't know if this is going to show up much at all, but let's try it. Where g of g, can you see that? You can see it all right. G of xy is equal to 2x. Okay. How will a contour interval of 1 look different? Well, g of xy equal 2x, your z value now, certainly when x equals 0, z is equal to 0, so you're back on the y-axis again, that's there. But then the next one, when x is equal to 1, g is equal to 2. So x equal 1, g now is up here at 2. And then, so it's going up like this. It's steeper this way, okay? So then if you did those map, you would put that on the xy axis and stood it up, then it would be every other one, they would be 2 apart, okay? For every one you go out in x, you go up 2 in z. So that would be in the xy plane, I think they would be 2 apart now. Okay, let's see how they describe it. On the contour map of that, the distance between the 2 adjacent lines is, I'm sorry, I said it backwards, is 1/2, because remember they're steeper, and you're plotting that down on the xy plane, so that would plot down in between this one, so they would be 1/2. So the steepness is this way, and the plotting on the xy plane would be down here. When you projected that down here, that would be at 1/2. So they would be 1/2 this thing. So you have 1, 2, 3, you know, 2 for every the plot down, because this is a much steeper axis. Okay. Wow. Homework exercises. Do either 1 or 3 or both. Any of the odds 5 through 11. Either 13 or 15 or both. 17 or 19 or both. Any of the odds 21 through 25. Do 27. Any of the odds 29 to 35. And they say 37 is sort of a writing exercise, but think through that one. 39, so do either 37 or 39. Then do either 41 or 43. Either 45 or 47 or both if you choose to. 49 or 51 or both if you choose. And then any of the odds 53, I'll just say 53 or 55. Either one of those or both if you choose. Okay. I'm glad to be out of that section. Okay. I mean, it's, I guess, good stuff, but okay, here we go. It's more just touchy-feely stuff. That's not what I wanted it to do, and it didn't. So now I'm going to have to go back in and open it up again. And we go to 210, right? Wait, are we done? 5, okay. Yeah, you're right, 5 minutes. Okay. Let's see if we can get started in 14.2. Not one of my favorites either, but at least it should be a little more familiar. I don't know why it jumped out of the whole chapter, just because I closed the last section. It's having that. Here we go. Okay, 14.2. Hopefully this is going to be somewhat familiar to you because it's very, very, very much like limits of continuity in 2 variables. Now we're doing it in several variables, if it'll ever come up. Here we go. Okay, we'll begin the slideshow from current slide. Okay. So this section develops limits in continuity in multivariable setting. We focus on functions of 2 variables, but with similar definitions and result applied to functions of 3 or more variables. Recall that in the real number line, the number x is close to a if the distance, absolute value x minus a, is small. That's what we mean, close to a. In a plane, though, a point xy is close to another point AB if the distance between xy and AB is relatively close to each other. In other words, if those 2 points are within a certain radius of each other. That's what it's talking about here. We haven't quite gotten to this figure yet, but this is what this figure is talking about. So on the x, if you just xy was all you're fiddling with, and you had x close to a, that means the absolute value between whatever value x is and a is relatively small. Now if you're talking about you have a point xy close to some other point AB, or they call this something else, PR, that's not really what, that's not the point, AB, then the x minus a squared plus y minus b squared, that distance is relatively small, okay? So now you're in the 2-dimensional definition, okay? Now, we're not quite at this slide yet, so let's go on. If we take all the points that are a distance of less than r from point P, say, here's your point P. You want all the points xy which are less than r away from P, where r is the square root of x squared minus a squared plus y squared minus b squared, okay, then that would be, put you within the circle, because the circle would be r is equal to a constant, and that would give you, if your xy is less than that, then the distance here is less than that. So you're everywhere within that disk. I've been calling it a circle, they call it a disk. Now, what do we mean by an open disk as opposed to a closed disk? Open disk means you don't necessarily count the boundary. Closed disk, you do count the boundary. So then, open disk, that the square root of x squared plus x squared minus a, x minus a squared plus y minus b squared, that square root is less than r, that would be your open disk. Less than or equal to r, that would be the closed disk. So if we put the disk with the asterisk on them, that then excludes the point P, okay? Not the open disk, that's what this is. That's the open disk. If you're excluding point P, then you put the asterisk by it. The open disk DPR consists of all the points x, y at a distance less than r, not less than or equal to, that would be a closed disk, less than r from P. It does not include the boundary circle. Okay? But if you're talking about the D asterisk there, that would be all the points in there, but not counting P. There's a reason for that. Are we out of time yet? Huh? Yes? Okay. We will be starting next time at your definition for limit. Okay? And this is very close, very similar to the limit that we had in 2 dimensions. So I don't think it's going to be anything super new to you. Got to find what my piece of paper is. Is that it? Nope. Oh, here it is. All right. We didn't get enough done to do any problems in that. We're going to try to make our way as fast through 14.2 as possible so we can get to 14.3, which to me is the heart of chapter 14. Let's get that done, and we'll move on from there. So I'll try to pick up speed a little bit here. Good deal. Thank you. Excellent. I forgot to ask the people who came in late, did you get a copy of the second test?
Yeah.
You did? Okay, good.